Bending tutorial. We're going to walk you through a typical exam style question that a lot of people struggle with. We're going to work out the maximum tensile and compressive bending stress induced in the beam. However, we're going to show a different approach to solve the problem that will hopefully help you understand the question a lot better. As you can see from the free-body diagram, there's 100 Newton meters acting on the 3 meters of the beam, and there's a point load of 200 newtons acting at the end of the beam at 4 meters. Considering the reaction forces AY and BY acting upwards as positive, we're going to work out the vertical forces acting along the beam. So AY plus BY minus the 100 Newton meters acting along 3 meters of the beam minus the 200 newtons acting at the end of the beam is equal to 0. So by doing this, we get an equation for AY plus BY is equal to 500 newtons. Secondly, as it's in equilibrium, we're going to take moments about the point A. So the sum of the moments about point A should equal to 0. So by taking the moments about point A, we're going to get an equation for BY. For 3BY minus, at anti-clockwise, we have 3 times 100 times 1.5, which is acting in the middle between A and B, minus 4 times 200 newtons equal to 0. So we can work out a value for BY, and BY is equal to 417 newtons. So by substituting the value we found here into the initial equation of AY plus BY is equal to 500 newtons, we can find the value for AY. So AY is equal to 83 newtons. So now we have a value for BY and AY.
So the beam that we're looking at is a T-shaped beam, and the distance from the centroid to the bottom of the shape is given, and is 48.8 millimeters. The distance from the centroid to the top of the shape is also given, and is 21.2 millimeters. We were also given the second moment area, which is IXX, and is equal to 582 times 10 to the minus 9 meters to the power of 4.
Now that we have calculated the reaction forces acting on the beam, we can go ahead and plot a shear force graph. Looking at the beam, we have an 83 Newton force acting at the start of the beam, so we can plot an 83 Newton on the graph. Then we have a 100 Newton meter UDL acting over a 3 meter length. So the time taken for the shear force to become 0 will be 0.83 meters, so we can go ahead and plot that on the graph. So as we have a 100 Newton meter UDL acting over 3 meter length, that would give a total force of 300 newtons acting downwards. We can subtract that from the 83 at the start to give minus 217 newtons, and we can plot that again on the graph. Then we can see on the diagram we have a force of 417 newtons acting up. So adding the 417 newtons to the minus 217 newtons will give you a force of 200 newtons, which again we can plot on the graph. Then looking at the diagram, over the next 1 meter length we have no force, so it's just a constant line, followed by a 200 Newton force acting downwards at the end of the beam, so we can plot that again. Now that we have plotted all the points on the graph, we can join them up to create our shear force diagram. Next, we're going to plot a graph for bending moments using the shear force graph above. To calculate the bending moments, we simply calculate the area under the graph of the shear force graph for each of the individual shapes. So the first shape is a triangle. So I do a half base times height. So that's a half times 0.83 times 83, and that gives 34. So we draw a curved line up to 34, and it's a curved line because it's a steep gradient. The next shape is also a triangle. So you do a half base times height again. So that's a half times 2.17 times minus 217, and that gives minus 235. Now, where most people make a mistake is that they actually do 0 minus 235, when in actual fact they should do 34 minus 235. So 34 minus 235 gives minus 201. So we're just going to draw a line going to minus 201 now. And finally, the last shape is a square. So to work out the area of a square, we do simply base times height. So that's 200 times 1, and that gives 200. Now, due to a rounding error in the previous answer, we get minus 201, but it should be actually minus 200. So minus 200 plus 200, and that gives 0. It should always finish on 0.
Okay, so we're now going to use information gained, all the calculations we've done, to finally put it into the final equation to get our answers. So we're going to use the formula sigma is equal to minus my over I. Our top centroid was 0.0212 meters, and our bottom centroid was equal to minus 0.0418 meters. And our second moment of area was equal to 582 times 10 to the minus 9 meters to the power of 4. Yep, so using the values we've obtained for m, which for the first time we're going to use is 34 Newton meters, we're going to plug all our values into this formula now. So we have minus 34 times 0.0212, and that's all over our second moment of area, which is 582 times 10 to the minus 9. We come out with a negative answer of minus 1.238. So for the bottom bit, we now have sigma is equal to minus 34 times minus 0.0418. That's all over 582 times 10 to the minus 9, and we end up with 2.442. Okay, I just made a slight mistake, sorry about that. It should be megapascals rather than pascals. Okay, so we're now going to calculate sigma for m equals minus 201 Newton meters. So we just plug the values again into the formula. So we have minus brackets minus 201 times 0.0212, and again that's all over the second moment area, which is 582 times 10 to the minus 9. We come out with a value of 7.322 megapascals. We now need to do the same for the bottom. So plugging the values again into the formula, we have minus bracket minus 201 times by minus negative 0.0418, and that is all over again the second moment of area, which is 582 times 10 to the minus 9. And we get a value of minus 14.44 megapascals. So as you can see, the values from the right hand side are much larger than the ones we've obtained on the left. So we're going to use the ones on the right hand side for our maximum tension and maximum compression. So our maximum tension came out to be 7.322 megapascals,
and our maximum compression came out to be minus 14.44 megapascals.